Welcome to this lecture series in group theory. In this lecture, we look at a general construction of actions arising from a given action. You'll see what I mean by that. And we will look at a very nice number theoretic application of that construction. It will be a very clever application, and I think today's lecture will be more complicated than usual. All we need to know is the orbit stabilizer theorem, and we have recalled it so many times that I don't want to recall it anymore. Here are three problems. They are not group theoretic problems, but mostly just some very general number theoretic exercise. You can use these problems to prove even stronger results than the one we will discuss. In fact, what I mean by that is you can strengthen the results that we will discuss, but I will not go into how to do that. But still, these exercises will be useful for you to understand number theory or group theory a little bit better. All right, so here is the general construction of actions that we want to discuss. So suppose X is some set, some set. We can think of it as a finite set if that helps. And K is some positive integer. Then we define a K subset of X as any subset of X of size K. So a K subset of X is just a subset of X whose cardinality is K. Very simple definition, nothing complicated. And here is a piece of notation. This is a notation to mean the set of all K subsets of X. And it's a meaningful notation. I'm sure you're familiar with this notation, n choose K. So n is some positive integer and K is some positive integer. N is greater than or equal to K, let's say. Then n choose K is supposed to mean the number of ways of choosing K different things out of n given objects. If you think about it, this is same as asking for the number of K subsets of a given n element subsets. Here what we are doing is we are not talking about number, we are just talking about the subsets, the K subsets of a given set X. So this is not a number. All right, just a piece of notation. And here is the general construction. So suppose we are given an action of a group on a set X. Then we define an action of G on the set of all the K subsets of X as follows. So for little g and capital G and a K subset of X, we define G dot S as G dot S is equal to G dot X, X and S. So this dot is what we are defining, and this dot is coming from the given action. These things can get confusing, I think, but I was never confused by them, and I don't think anyone is ever confused by them. One just has to remember that this dot refers to a different action, and that dot refers to a different action. All right, so out of a given action, we are constructing sort of a bigger action, which is given by this very simple thing. Clearly, this is an action because if S is a K subset, then so is this, right? Because after all, this map, the reason is very simple. The reason is just that the map X to X, which takes little x to G dot X, where little g is fixed, this is a bijection, right? And therefore, a K subset will go to a K subset under this map. And this is nothing but the image of S under this map. And hence it is a K subset. So that's that. So at the very least, this definition takes a K subset to a K subset, and you can check the two axioms of group. Two axioms of group actions. So if G were the identity, then clearly this is same as the set X. And the other thing is G1 dot G2. You can easily verify that. Of course, you'll use the fact that the given thing is an action. Okay. There's something else that I wanted to say. All right, I can't think of anything. Yeah, so maybe, yeah, so I wanted to note that X choose 1, meaning the set of all the 1 subsets of X is essentially X, one slight difference is the following. So suppose x were equal to, let's say, 1, 2, 3. What is x choose 1? The set of all the 1 subsets of x. So that is actually this set. It's only artificially different from the set x. So you can kind of just think of them as the same things in an obvious way. And once you are given an action of g on x, the action of g that you get on x choose 1 is essentially the same action as you had on x. It's just a nomenclature difference. Nothing of essence is different. All right, so this is a general way to construct a bigger action out of an older action. And now we will look at an application of this via a very clever proof. So first, let me state the theorem that we want to prove. It is called Babbage's theorem, and I think this is the same Babbage as Charles Babbage, the one who is thought of as the father of modern computer. All right. So suppose we are given two positive integers a and b, where b is at most a. Then recall that nothing to define here. Recall that this a choose b is equal to a into a minus 1, a minus b plus 1, divided by b to b minus 1, 2 dot 1. Yeah, I think this is correct. Yeah, this is correct. And of course, this is not, I mean, this is not the definition of a choose b. A choose b is the number of ways of choosing b objects out of a given object. It turns out to be equal to that. All right. So now, Babbage's theorem states that if we start with a prime, and I think this is not important in Babbage's theorem, this hypothesis that the prime is greater than 3, but let me just keep it here for safety. So start with a prime at least equal to 5. Then whenever we are given two integers a and b with a exceeding b, we have this congruence equation. AP choose BP. AP is just the multiplication of a with p and so on with b. So AP choose BP is congruent to A choose B modulo p square. So in particular, this shows us that 2p choose p is congruent to 2 modulo p square. Something that is not obvious, and you can play around with this, substituting values for a in place of substituting values in place of a and b, and you can get very non-trivial congruences. All right, so we'll prove it using machinery of group actions. So we will start with a certain very strange looking action. So let g1 equals ... ga equals z mod pz. So we have made a copies of the group z mod pz, right? And at the same time, we'll make a copies of the same thing, but this time we'll think of them as sets. Okay, so we have made a set of a copies of z mod pz and then another set of a copies of z mod pz. Let G be the product of all the groups, and here is the thing: X is the disjoint union of all the xi's. So what does this mean? Well, if I just took the usual union, what I would get here is z mod pz, because all of these xi's are same. Here, when I write it this way, all I mean is forcefully think of them as separate. So one formal way to achieve that, and this is just one of the ways, is to instead write this as x1 cross 1 usual union, x2 cross 2 usual union ... xa cross a. So that's the formal way to think about it. But I think it's just better to think of this as, you have the same object, you have made a different copies, and you have a way to discern. When you pick an element from this, you have a way to discern in which part or which xi the chosen element lies. So the size of x is AP, and the size of G is p to the power a. Right? So I hope these definitions are clear. There is no problem here. Maybe here there is room for some confusion, but I've tried my best to dispel it. And now we define an action of G on X. Define an action of G on X as G1 comma dot 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 GA dot X is equal to GI dot X if X in Xi. So you pick an element from X. It is going to lie in one of these, exactly one of these Xi's, and you pick a group element, an element in the group G. So whichever I is the one which holds X in it, or rather whichever Xi holds little x, you just find that coordinate, and here I meant to write Gi plus X. So once again, if suppose this lies in Xi, you just look at what is there in the ith coordinate. In the ith coordinate there is Gi, and add them like group elements. So after all, an element of Xi is just an element of Z mod Pz. Gi is also an element of Z mod Pz, so it makes sense to add them, and just add them. Right. So the other coordinates, they have no job once you know the coordinate of X. So again, I hope this makes sense, and let us look at a picture of what's going on. So here we have an example where the prime is of size, the prime is equal to 5 and a is equal to 3. So we will make three copies of Z mod Pz that we have made here. So this disjoint union is our set X. This is X. And the group is product of which one cannot draw. I mean, it's too complicated. So what's happening is, suppose I'm given some group element, let's say, whatever, 2 bar, comma, 4 bar, comma, 3 bar. This is my element of the group, which is of course equal to Z mod 5Z to the power 3, because A is equal to 3. So 2 bar, comma, 4 bar, comma, 3 bar, when acted on some element of X, let me just put it as little x. And suppose this X is, let's say, maybe this one. Suppose this is my X, the orange one. So what I will do is, I will just take the first coordinate and add it to this guy. So if I add it, I get here, because 2 bar plus 1 bar is 3 bar. So what you're doing is you're just rotating this ring, whichever ring holds the element X. You're just rotating this ring by what is there in the first coordinate and taking the image under that rotation. So basically these are independent rotations of these rings, and this just tells you which ring holds the element X, and correspondingly you get another element in the same ring which it belongs, in which this guy belonged. So that's the action. It's not clear why we are even considering it, but you can see that at least one of the characters that appear in this Babbage's theorem are appearing here, and soon more characters will also appear. So this is just some action, and now what we will do is we will consider so the action of G on X gives rise to an action action on X, choose BP. So BP is all the BP is all the subsets of X. So what am I saying? X choose BP is the collection of all the subsets of X of size BP. Right? We discussed this. So once you're given an action of this sort, we get an action of this sort. This is what we saw earlier, and this is the action that we will use ultimately to prove Babbage's theorem. All right. So first thing to note is that here is the first thing to note: each orbit of this action has size p to the k for some k. Why is that? Just apply the orbit stabilizer theorem. So you pick some x in, not, let me not call it x, let you pick some s in this guy. It has some orbit. The cardinality of that orbit is the stabilizer of that element, the index of the stabilizer of that element. And since G is a group whose size is p to the power something, this also has size p to the power something by Lagrange's theorem, because this is a subgroup of the group G and hence divides the cardinality of G. So since G has the cardinality of G is a prime power, so is the cardinality of the index of any subgroup of G. So this is the any orbit has size p to the k for some k, and this has nothing to do with what lies here. It is all about the group G. So this is some simple comment, and we will use this notation. Let nk be the number of orbits of size p to the k. Okay, and thus the size of the set on which we are acting is same as n0 p to the power 0 plus n1 p to the power 1 plus n2 p to the power 2 plus dot dot dot. Of course, this is a finite sum because the set is, everything is finite. The situation is, this has to terminate somewhere. You cannot have an orbit of size more than p to the power a, for instance. So this is a finite sum. And yeah, so let me just write it then. This will not go beyond this point. All right. Why is that? This is simply because orbits partition the set x choose bp. The orbits partition the set x choose bp, and so here we have all the orbits of size 1, and n0 is the number of such things. So we have accounted for so many elements. Here n1 is the number of orbits of size p, and each orbit has p elements. So the total number of elements we are accounting for is this much, and so on. So this is a very simple thing. We saw a baby version of this fact when we were proving Cauchy's theorem using machinery of group actions previously. All right, so we have that, and we go modulo p square. So we get ap choose bp is congruent to n0 plus n1p modulo p square. So we are getting there. This is what we were trying to understand in Babbage's theorem. This is equal to that, so I should have mentioned it. X has size ap, right? We said that x has size ap, and hence this has size that much. And in the right hand side, these all go away when we go modulo p square. So we have this guy. And now here are two claims. We claim that n0 is equal to a choose b. So let's prove this claim. Why is this true? So basically, n0 is the number of orbits of size 1. So we want to count those things whose orbits have size 1. So let s equals s1 disjoint union dot 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 sa be in the set we are acting on, such that orbit of s has size 1, meaning orbit of s is just the singleton s. And when I write things this way, I just mean s1 is a subset of x1, and so on. Sa is a subset of xa. I'm not formally writing it, but I hope that's understood. So if we have an element whose orbit has size 1, what can we say about that element? So here is what we will show. We will show that Si is either empty or equal to Xi. So each of these, so S1 in particular is either equal to X1 or is empty, and so same for S2 and so on. And once we establish this particular line, it will be clear that N0 is indeed A choose B, because then how many such S's can you form? The S that we have to form has to have size BP, because that's what, the size of S has to be BP. It's an element of this after all. And what this shows is that either you are fully saturated in a given component or not, So it's a question of choosing which xi's you are fully choosing and which you are rejecting. And out of these a coordinates, you will be fully choosing some b coordinates and rejecting the other. So therefore, you will have exactly a choose b choices. All right. So that's why this will imply. And clearly, once you have any such thing where you fully choose some b of the xi's and reject the others, each of those clearly have orbit of size 1. So with that remark, let us prove this. So suppose uh, S1 is non-empty and at the same time is properly contained in X1. So then we want to produce a contradiction, basically. And you can replace S1 by Si and X1 by Xi. So in this case, what happens is, just consider the elements of the sort G, 0, 0. This dot S is what? This is just G plus S1, disjoint union S2, disjoint union SA. So that's how G acts. And when I say G plus S1, I just mean G plus, what should I write? Maybe G plus little s, G plus little s, where little s is in S1. So that's what that set is. So this thing, G plus, so this implies that G plus S1 is equal to S1 for all G in the group Z mod PZ. Why is that? Because since the orbit of S is size 1, this is same as S, and since this is same as S, this should be same as S1, that should be same as S2, and that should be same as SA. So the last coordinates don't offer any resistance, but from this we deduce this fact. So G plus S1 is equal to S1 for all group elements, but this has to force, since S1 is non-empty, this forces that S1 is actually full. And that implication is not hard. That is simply because you can just take G equals 1 bar and you will see why this is so. If there is anything missing, you can get it here. So I hope this reasoning is clear. So what we have shown is that S1 is either empty or full, same for S2, same for S3, and therefore the structure of S is just you're choosing some B of the xi's fully and rejecting the others, and hence this is established. Okay, so the second claim is the following. N1 is 0. And you can prove this in exactly the same way as we did this. You just start with some arbitrary element, and you will see that if it so happens that you have two non-empty, okay, so let me at least hint how this is done. So say S equals to S1 disjoint union SA is such that orbit of S has size P, then if Si, if there exist I and J, meaning two different coordinates, such that Si is non-empty and properly contained in Xi, and same for Sj, then you can show that orbit of S is actually at least P square. And the reason is just like in the previous thing. Here you just worry about group elements of this sort: 0 dot dot 0 gi, 0 dot dot 0 gj. And if you just keep hitting the set S with these group elements, you will see that you're producing at least P square different things, because individually in the ith part you will be producing P different subsets, and in the jth part also P different subsets, and you can do that independently. You can rotate them independently, and hence you'll be producing at least P square such things. So this is a rough way, just a rough argument. This is not a proper formal argument, but it is just best to execute this argument for oneself rather than me doing all the details. So this turns out to be 0, and hence, thus we get AP choose BP is congruent to A choose B modulo P square. So using the machinery of group actions, we established something so interesting, purely number theoretic. And let me just end this with one remark. You can prove something stronger. This is called Wolstenholme's theorem. So fix a prime P at least 5. Then for any two positive integers A and B with, let me just say, A and B with B less than equal to A, we have this congruence. So here the modulus is P cube rather than P square. So it's stronger. And the same proof goes through. We've already seen n0 is this much, n1 is that much, but n2 turns out to be this horrible thing. It's if you just think about it this way, the way we have been calculating n0 and n1, you will find this, that this is equal to that, and then you can prove this theorem. So that's very nice. Look at the Wikipedia article. So look at the Wikipedia article on Wolstenholme's theorem. There is some more things are given in that article. And you will also see the use for these exercises when you look at that Wikipedia article. Okay, so fairly complicated lecture, but I hope it was worth your time. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.